Sample 7-8 is a ski jump. Can be found on page 310 in your textbook. I've recreated the drawing here. We've got a skier starting at this initial position in the top left at a height of h above the ground, which I'm calling h equals 0. He's going to finish over here on the right near the F with a certain velocity at height capital D above the ground. So we're going to use the work energy theorem to find an expression for his speed when he launches in terms of some of the parameters of the problem and also the gravitational constant. So we know from the work energy theorem that any work done on the skier is equal to his change in kinetic energy, plus his change in gravitational potential energy, plus the change in his internal energy. Now we're told in the problem that we can ignore friction and air resistance, and so that's really telling us that we can set internal energy equal to 0. If we choose the skier plus Earth as our system, then the work done by the gravitational field is internal, and we can also say that the work done on the skier is equal to 0. And you'll see this in the more problems you watch and the more videos that I link for you, that when there's gravitational potential energy involved, including the Earth in your system usually helps. So we're going to go ahead and do that. And so what we have here is 0 equals the change in kinetic energy plus the change in gravitational potential energy, plus 0, I suppose, for continuity there. So we're pushing towards conservation of energy, which is where we're going in the next topic. But what we have here is that the change in kinetic energy is opposite the change in gravitational potential energy. So let's go over here and let's make an accounting of all of the energy we have at the top and at the bottom. At the top of the ramp, the initial kinetic energy is 0 because he's at rest. At the top of the ramp, the gravitational potential energy is mg times capital H because here his height is capital H. Now, at the bottom of the ramp, or I should say at launch, things have changed. He's now got a speed, so his kinetic energy is 1/2 mvf squared. His final gravitational potential energy is mg times capital D right here. Okay, so we have, let's go on to the next page here. We have our change in kinetic energy is opposite our change in gravitational potential energy. So we have 1/2 mvf squared minus 1/2 mvi squared. That's our final kinetic energy minus our initial kinetic energy. Yes, I know that 0 will make things a little bit more simple in a moment. All right, negative. What's our change in gravitational potential energy? We're ending at mgd, and we started at mgh. So I like to keep all the negatives where they should go at the beginning. I don't try to get too fancy from the get-go. I like to make an accounting of all of the energy we have, set what's equal to what's equal. So now let's get rid of the 1/2 mvi squared and have 1/2 mvf squared on our left-hand side here. Now if I have this negative sign outside, that just means I can switch the order of these, mgh minus mgd. Okay, so we notice that the mass cancels out, and you probably expected that. Let's bring the 2 over to the other side. Vf squared equals 2. Let's factor out a g and call that h minus d. And that lets us do one more step. The square root of 2g times h minus d. And we can tell that this is going to be a positive number because h is bigger than d, so h minus d will be positive. G is positive and 2 is positive. So it's good to have like a mental check there. This is what I was kind of talking about when I said make sure your answer makes sense. We're not going to take square roots of negative numbers in this class. So the fact that VF is positive is a good idea. And a wrong answer there could point to a mistake that you made up here with the negative signs, because I do that sometimes. So we'll solve this problem the same way, but we'll just call it something different when we talk about conservation of energy. But that's how we use the work energy theorem to find out the speed of the skier when he launches.